Model consists of PV panel, battery, supercapacitor, DC load, and inverter, and then AC load and grid. Okay, so this PV panel, right? So here we are using 2000 watts PV panel. That means the single panel power will be 250 watts, and then here we are using 8 panel in series. So totally it can generate 2000 watts. Okay, and single panel voltage will be 30.7. So the terminal voltage of the PV panel will be 30.7 into 8. And then this PV panel will be connected to the DC bus or DC load via this boost converter. So this boost converter going to be controlled by means of P and MPPT. So here we are using that P and MPPT. So P and MPPT receive two inputs. One is PV voltage and current. Okay. So inside that P and MPPT, you can see here, right? So we have to provide the 4 parameter. So these are the 4 parameters, that mean initial duty cycle, maximum duty cycle, minimum duty cycle. Okay, minimum duty cycle, and then increasing or decreasing duty cycle value. Okay, and then in order to implement P and MPPT, right? So we have to initialize previous voltage and power and duty cycle. So for that, here we are using this value V volt, P volt, D volt, nothing but the previous instant voltage, power and duty cycle. So initially it is does not have any value, right? So for that, so here we are making V volt, P volt equal to 0 and D volt equal to, we are going to consider initial duty cycle. Okay. So next here we are calculating power by multiplying PV voltage and current, and then we are calculating dV and dP. So change in voltage, change in power by comparing current instant voltage with the previous instant voltage and current power with the previous instant power. So next you have to check the change in power. If change in power less than 0, again you have to check the change in voltage. So if change in voltage is less than 0, you have to decrement the duty cycle. Okay, that means you have to adjust the terminal voltage of the PV panel in order to get the maximum power from the PV panel. So here the terminal voltage will be adjusted by means of increasing or decreasing the duty cycle. So based upon this condition, dV is less than 0, dV is less than 0. Okay, if suppose dV is not less than 0, again you have to check dV only. Here the condition will be reverse. So for this condition you have to decrement, and here we have to increment. So here you have to take increment and decrement. Okay, so based upon this dV and dV, that increment decrement going to be, that means duty cycle will be vary, and that's why we can adjust the voltage of the PV panel to extract the maximum power from the PV panel. So after calculating the duty cycle, you have to compare with the duty cycle with the maximum minimum duty cycle value. So within this, and that means duty cycle, that means calculated duty cycle is within that limit, no problem, no need to do anything. So if it is not obey that the maximum minimum limit, you have to maintain the duty cycle which is equal to previous duty cycle. So here we are going to override the current duty cycle voltage power with the previous duty cycle voltage and power. So this will be keep on executing not to extract the maximum power from the PV panel. Okay, and next we go with the that means here we are using battery. So the battery here will be 300 volt. We are using 300 volt battery, 48 Ah. It's going to be connected to the DC bus via this bidirectional converter. Same here you can see that we are using supercapacitor. So supercapacitor voltage at 300 volt, and then it connected to the DC bus via this bidirectional converter. Okay, so these both bidirectional converter, right? The bidirectional converter of the battery and the bidirectional converter of the supercapacitor going to be controlled by means of voltage and current control method. So here you can see that. So here we need to measure the DC bus voltage, and then it's going to be compared with the 400 and processed via PA controller, and then PA controller is going to be processed via filter. Okay, so this filter output of filter will be act as a reference current for that battery, and then you have to take the difference between the output of filter and output before the filter, right? You have to take difference, so this will be act as the reference current for supercapacitor. Okay, and then this reference current going to be compared with the battery current, and this reference current going to be compared with the supercapacitor current, and then it's going to be processed via PA controller. So this PA controller will be generate the duty cycle, and then it's going to be processed via PWM generator. Okay, so this will be generate the pulse. Okay, so this pulse going to be control this bidirectional converter in order to charge and discharge the battery according with the power balance in the system. Okay, and also here you can see that the output of P into MPPT will be duty cycle. So this will be processed by a PWM generator. It will be generate the PWM pulse. Okay. So this pulse going to be control this boost converter not to extract the maximum power from the PV panel. And then in the DC bus we are connected with the inverter and load. In this point we are having grid. So here we are going to control this inverter in order to connect with the grid by means of inverter control. So here we have the inverter control going to be controlled by means of current control concept. That means we are going to generate the reference current. Okay, so reference current, that means for example, so if power of PV is more than 800 watts, okay, more than 800 watts, okay, if power of PV is more than 800, right? So that means the reference current we are generating will be IL uh, if power of PV is less than uh, 800, right? We are getting the power from the grid. Okay, so this is a concept we are using here, right? And then here you can see that means the PV power is more than 800. We are supplying power from that PV battery and supercapacitor. So when PV is less than 800, we are getting power from the grid. So that will be processed via here. Okay, and then it will be magnitude, and then it going to be multiplied with the sine and cosine. So sine and cosine going to be generated by means of PLL. Okay, so here we are using PLL. So this PLL will be take care of frequency control of the system, grid and that mean inverter system. Okay, so because this PLL will be follow the frequency of the grid. Okay, so automatically the frequency of the system going to be controlled here. So here it will be used for generating sine cosine. So reference current going to be multiplied with the sine cosine, and then you will get a AB quantity. That AB quantity converted into DQ frame, right? DQ control concept. Okay, we are going to convert to AB to DQ, and then here we are measuring the inverter current. Okay, so that inverter current will be converted into AB to DQ form. So this is reference DQ, and then this is actual DQ. So we will be compared and processed via PA controller. Okay, so this is PA controller. The final output of this controller will be in the form of D and Q. So the D and Q will be converted into AB form, and then you have to take only A quantity. Okay, so this A quantity going to be considered as a modulating signal. So that modulating signal going to be processed via this PWM generator, sinusoidal PWM generator. So it will be generate the pulse. So this pulse going to be used for control this inverter, not to that will based upon this reference current. Okay, so this model working of this model. Okay, now we can see the result. So here you can see that. So this is PV measurement, and then this is battery measurement, and then this is supercapacitor measurement, and then this is AC load, and then this is grid power, grid voltage, current and power, and then this is DC bus voltage, current and power. Okay, so this is inverter voltage, inverter current and grid current. Okay, so here you can see that we are getting sinusoidal output, right? That means here you can see that. So for changing irradiation condition, right? We are changing irradiation from 1800, 500, right? So what happened? The PV power is decreasing. Because of the decreasing PV power, what happened? Batteries try to supply the power, and also here you can see the supercapacitor, right? For during that change, right? Change of irradiation. So because of change in irradiation, what happened, right? And the power will be decreasing. During that time, the supercapacitor will be supplying some power and then comes to zero. Okay, so that mean as per that mean the peak load or load power balance is changing in the system, so that going to be overcome by means of supercapacitor. Okay, so here you can see that. So now you can see that the PV is goes to less than 800. So what happened now? The grid supplying power, right? Grid supplying some power. Okay, a grid supplying around 1500. Okay, 1500 watts. Okay, so now grid supplying some power to the system. Okay, so because PV is having less than 800 watts, so that's why PV is supplying some power to the system. Okay, so this is a working of model, and then if we change the MPPT, right, so we will see the difference in the uh, PV power, right. So here you can see that for 1000 watts meter square is around 1900, 900 only we are getting, right. So we will see the difference for comparing of different MPPT algorithm. Okay, so this is for P and O MPPT algorithm output. So next I'm going to simulate incremental conductance. So this is a model for incremental conductance in MPPT. Same thing, but we are using incremental conductance. Okay, I used only incremental conductance in BPT. So here you can see that same way as P and in BPT, what initialize initial duty cycle, maximum duty cycle, minimum duty cycle, increase and decrease in the duty cycle, and then here you have to initialize V volt, P volt, D volt, I volt, and then you have to provide value for V volt, P volt, I volt, and the D volt, and then here you have to find power, and then you have to find dv iv, and then here you have to check dv first, whether dv equal to 0 or not, and then you have to check di equal to 0 or not. If both are equal to 0, that means already PV panel is operated at maximum power point, so no need to change any changes in the duty cycle. If di is greater than 0, so you have to decrement the duty cycle, or else you have to increment the duty cycle in order to adjust the terminal voltage of the PV panel in order to get the maximum power from the PV panel. And also another condition for the incremental conductance. So here you have to compare the incremental conductance dI by dV equal to minus I by V. So both are equal means, so already PV panel operated to maximum power point. So if this condition, the dI by dV is greater than minus I by V, you have to decrement the duty cycle, or else you have to increment the duty cycle. Okay. So based upon this condition, we are going to get the maximum power from the PV panel. So this is known as incremental conductance in conditions. Okay. and then every time you want to override the current duty cycle voltage power current to the previous duty cycle voltage power and the current. Okay, so it will be work accordingly with that coding. Okay, so same thing, same condition we created here. So next we got to compare the result of PV, right? Because we change the uh, PV power only. We have to wait for 1 second. That means up to completion of this. Okay. So here you can see that the difference of the power of P and MPPT and incremental conductance, right? You see that, right? So here also I'm going to use print to figure option and then save the figure, right? So this is for incremental conductance. You got to simulate for full 5 seconds and then you take print figure option, right? So for example, I'm providing the detail now. So now I stop this simulation, I close this one. Next, I'm going to open modified incremental conductance. Here we use modified incremental conductance. So only thing, so here we are using one term nothing but m. So the m nothing but we are calculating m equal to absolute value of d v by di. Okay, so that m going to be multiplied with here, right? M into m star delta t, m star delta t. So this is a modified version of that incremental conductance. Okay, so same like of incremental conductance, only we have to multiply this m parameter in the delta t. So it's a modified version. So it will be provide a better result than incremental and paying on to MPPT. So here I'm going to simulate this model and then you have to check the PV power. So this is the result of modified incremental conductance MPPT. Okay. So now I'm take this picture, the print here, and then now I'm going to combine three figure, right? So this is for PSO and figure 2. So this is for incremental conductance. So now I'm going to take so edit button, this edit button, click this edit, and here I'm going to change color to some other color, red color. Here I'm going to change the color to purple color, and then I'm going to copy this one and paste it here, and then I copy this one and then paste here. Now we can see the difference, right? So this incremental conductance having maximum power, right? Some of the point you can see that. So we will get the maximum power than normal modified incremental conductance will be provided the better result than incremental and P and MPPT. So here you can see that. So they have highest value, right? So this is the difference of this 3 MPPT. Okay, so you can provide this result like that, and also you can compare other result also by taking print figure and then combine that figure in single. Okay, so thank you.